I welcome you to this class of econometric methods. Myself, Dr. Muhammad Imdadul Haq, an associate professor at the Department of Economics, Aligarh Muslim University. In our previous lecture, we were discussing the case of stationarity. We have seen what is the importance of stationarity in econometrics, particularly time series econometrics. And we have also taken a particular model, that is the random walk model, and we have tried to identify whether it is a stationary process or a non-stationary process. While doing this identification, we have taken three different types of random walk models: the simple random walk model, without drift and without trend. The second one was with a random walk model with a drift parameter, and the third one was random walk model with random walk model with both drift and trend. And we have seen that in the first case the mean was okay, but was fine, but the variance was not constant, it was changing with time, so it wasn't an stationary process. Next, we saw the second one, it was with drift, and we saw that the variance, the mean itself was changing with the time, and in the last one also the mean was changing with time. So we need three things, we need three conditions to be satisfied for stationarity. That is, the mean should be constant, the variance should be constant. In today's lecture, we will be taking a different type of model, particularly known as autoregressive model, wherein we will be trying to prove, and we will try to not only prove, but we will try to check whether it is a stationary process or a non-stationary process. So obviously our today's lecture also, it revolves around the concept of stationarity, which is a stochastic process. A stochastic process is said to be stationary if its mean and variance are constant over time, and the value of the covariance between the two time periods depend only on the distance between the two time periods and not on the actual time at which the covariance is being computed. We have seen the things like it is mean reverting, it has a finite variance, it has a finite memory, that is the impact of a shock dies out with time. Now we move on to this autoregressive model. See, autoregressive model is based on the philosophy that let the data speak for itself. And it is not necessarily based on any economic theory. It's basically a modeling framework in which YT is based on its past values only. So if you want to define autoregressive model, here YT is generated by a weighted average of past observations going back P period together with the stochastic term. So we are seeing theta 1 YT minus 1, and then there is a correction over here, that should be 2 theta 2 YT minus 2, and it will extend up till here. We use the notation P for autoregressive model. How many terms are there? If there are 10 terms, then the value of P would be 10. If there are 2 terms, the value of P would be 2. Now here we have an parameter mu. Now it relates to the mean, but it is not exactly the mean. But mu is not the mean of the process. Like say if mu is not equal to 0, it means that mean is not equal to 0, but it is not exactly the mean of a process. So this is how you define an autoregressive model, where YT is equal to mu plus phi 1 YT minus 1 plus phi 2 YT minus 2 plus phi 3 YT minus 3, and as many lag terms you want to incorporate over there. Now, if we recall our discussion on on the model which we have seen, the random walk model, while discussing the concept of stationarity, we have seen that phi was not present over there, theta was not present over there. Or you see, if a random walk model is something like this, YT is equal to YT minus 1 plus epsilon t. And here this if it is phi or theta, whatever, we assume that this is equal to 1. Then only we can write if phi is equal to 1, yt is equal to yt minus 1 plus epsilon t. And we know that this process is stationary, not stationary, sorry. We know that this process is not stationary. This is a random walk model. Herein, we are having this theta 1 and what I am defining it that theta 1 should be less than 1 if the process is to be a stationary process. We will see to it that suppose we have a model that yt is equal to sigma plus theta 1 yt minus 1 plus epsilon t. So we define an AR model as yt is equal to delta plus theta 1 yt minus 1 plus epsilon t. Now if you take the expectation of yt, when we take the expectation of yt, we take all the expectation, mu being a constant, it comes as it is. And now the process, since we are assuming the process to be stationary, what we say that expected value of yt is equal to expected value of yt minus 1 is equal to expected value of yt minus 2, and likewise. So that is why we are simply writing this as theta 1 yt minus 1, we are writing it as theta 1 mu plus epsilon t. So now we can define, excuse me, this should be delta over here. So now we define this process like this expected value of yt, expected value of yt is equal to delta plus theta 1 u plus epsilon t. Now this we can write it only in terms of, if we take this epsilon t, expected value is also 0. So what we are left up with is only expected value of it is equal to delta plus theta 1 u. This we write it as u is equal to delta plus theta 1 u. We take the mu to the left hand side. So we have mu minus theta 1 u is equal to delta. So we can write mu is equal to delta 1 minus theta 1. We have simply derived the value of mu. Mu is equal to delta upon 1 minus theta 1. Now this delta divided by 1 minus theta 1, it gives the condition of stationarity. Suppose what we are saying, theta is equal to 1, like it was there in our random walk model. If theta is equal to 1, and then what is left? Delta divided by 1 minus 1, that is equal to delta by 0, and delta by 0 is something which is infinity. So it's not constant. So if the condition of stationarity is this value, it should be less than 1. If it is less than 1, only then this like what we have a model yt is equal to, say this model theta yt minus 1 plus epsilon t. So this theta should be less than 1, only then it will be a stationary process. Now we take the basic model, the simplest model of autoregressive one, where we are taking only one lag, that is the value of p is only equal to 1, and the condition of stationarity is also being satisfied, that is theta is less than 1, that we satisfy the condition of stationarity. We have taken the basic model yt is equal to theta 1 yt minus 1 plus epsilon t. Now this characteristic epsilon t, this we refer to, it should be a white noise error term. The characteristics of white noise are expected value of epsilon t 0, variance epsilon t sigma square e, and covariance, that is epsilon t minus 1 is equal to 0. So if these three conditions are satisfied, we call it a white noise error term. So we assume that the error term over in the autoregressive model is white noise as the certain conditions are fulfilled. Now we take the model yt is equal to theta 1 yt minus 1 plus epsilon t. Based on this model, we first define y1. y1 will be theta 1 y1 minus 1, that is equal to y0 plus epsilon 1. Now we write y2. y2 is equal to theta 1 y1 plus epsilon 2. Now theta 1 y1 we have just now defined over here. We put this value inside in place of y1 in the second equation. So yt is equal to theta 1 bracket open theta 1 y0 plus epsilon 1 plus epsilon 2. Now when we open the bracket, we can write it as theta 1 square y0 plus theta 1 epsilon 1 plus epsilon 2. So this is our final term for y2. Now we define y3. y3 is equal to theta 1 y2 plus epsilon 2. Now in place of y2 we write this entire term. So y3 is equal to theta 1 bracket open theta 1 square y0 plus theta 1 epsilon 1 plus epsilon 2 bracket close plus epsilon, sorry, this will be epsilon 3, excuse me, please note this correction. So this we can write it as, when we open the bracket and multiply all the terms with theta 1, y3 is equal to theta 1 cube y0 plus theta 1 square epsilon 1 plus theta 1 epsilon 2 plus epsilon 3. This can be written in the general format as, we can go on extending for y4, y5, y6 and likewise. So we can write it as yt is equal to epsilon t plus theta 1 epsilon t minus 1 plus theta 1 square epsilon t minus 2 extending up till theta 1 raised to the power t minus 1 plus theta 1 t y0. Now these two terms towards the end, that is theta 1 yt minus 1 and theta 1 t y0, when your t is very large, when you have taken a very large time series data, then these two terms, this one and this one, they will tend to 0 because they become very small and they will tend to 0. So when theta 1 has a value of less than 1 and more than 0, as t tends to increase infinitely and it reaches infinitely, this term yt theta 1 t minus 1 and theta 1 t y0, they will become 0. So we are left with only this much. So we say that yt is equal to epsilon t plus theta 1 epsilon t minus 1 plus theta 1 square epsilon t minus 2. So that's why we define it as yt is the weighted sum of past shocks like et minus 1 and et minus 2 and et minus 3 and likewise. So it is the weighted sum of past shocks. And the shocks are of such a nature that they decrease as we incorporate more or more lag or as we move back to the past. So remote past has less influence in the realization of yt and the near past has a bigger weight or a larger influence. Again, the expected value of et and et minus 1 and et minus 2, as we go by our normal assumptions, they are 0. So expected value of yt is equal to 0, because when we take the expectations, expectation of this 0, expectation of this 0, expectation of this is 0. So this is a case of a zero mean, your expectation, your zero mean process. Although it's not very common in, you don't find it very often in your in economics series, but this is a type of process. Now let us check its variance also. Now variance is, what's the formula for variance? The expected value of yt minus expected value of yt whole square. So we have seen earlier that expected expected value of yt is equal to 0. The mean is 0. And what is yt? Yt is just an weighted sum of the past shocks. So we write it as epsilon t plus theta 1 epsilon t minus 1 plus theta 1 square epsilon t minus 2 and likewise and the whole square of it. It means we can write this as sigma epsilon square plus theta 1 square sigma epsilon square plus when we do the square over here it becomes theta 1 4 theta 1 raised to the power 4 sigma e square. So we have this variance of Et. Now this is variance of Et is sigma square. So this we can write it. What is the common? This term is common in all of them. So we take out in the common outside and we write it as here it is 1, here it is theta 1 square, here it is theta 1 4. So we write it in this format, that is variance of yt is equal to sigma epsilon square bracket open 1 plus theta 1 square plus theta 1 raised to the power 4 and likewise. So this is basically a infinite geometric progression where the first term is sigma square epsilon and the common ratio is theta 1 square. So based on that information we can write that the variance of yt is equal to sigma square epsilon divided by 1 minus theta 1 square. There is no t over here. There is no element of t over here, meaning thereby the variance is not changing with time, that is the variance is constant. Mean was equal to 0, variance is constant. Now we check the third property, that is what is happening with the covariance. Mean and both the mean and the variance, they are indicating that the process is stationary. Now we move on to the case and we are checking that whether the process is stationary or not. So we have Et, if you remember, Et was equal to epsilon t plus theta 1 epsilon t minus 1 plus theta 1 square epsilon t minus 2. From this Et we try to derive the function for, from this Yt we try to derive the function for Yt minus 1. So Yt minus 1 we simply add a lag. So is equal to epsilon t minus 1 plus phi 1 epsilon t minus 2. 1 becomes 2, here 1 is incorporated, here 2 becomes 3 and phi 1 square epsilon t minus 3. And we can go on writing this. So for covariance what we need Yt minus 1. The expected, so we write covariance now in terms of Yt and Yt minus 1. So expected value of, first we write the expected value of Et plus theta 1 Et minus 1 plus theta 1 square Et minus 2 and likewise the terms for Yt, bracket close, another bracket opens up and then we write the terms for Yt minus 1, that is epsilon t minus 1 plus theta 1 epsilon t minus 2 plus theta 1 square epsilon t minus 3. Now see, an error term is not related with this previous error term. So epsilon t minus 1 is equal to 0. So when we are opening up the bracket, when we multiply epsilon t with epsilon t minus 1, 0. Epsilon t with epsilon t minus 2, nothing, 0. Epsilon t with epsilon t minus 3, they are error terms of respective period, so that goes away. Next, theta 1 epsilon t minus 1 and there is a term over here also epsilon t minus 1. So we get a term theta 1 Et minus epsilon t minus 1 epsilon t minus 1, we write it as sigma square epsilon. Now we take epsilon epsilon t minus 1, we try to multiply it with, here it is Et minus 2, nothing. Again we take this term, we multiply with Et minus 3, nothing, 0. Now we take for Et minus 2, Et minus 2, Et minus 1, 0. Et minus 2, Et minus 2, yes, we get a term. So here there is phi 1 square and here there is phi 1, means hidden raised to the power 1. So we can write it at phi 1 raised to the power 3, Et minus 2 and Et minus 2 and Et minus 2, we write it as sigma square epsilon. So likewise, when we keep on adding the terms, except for one case, all the cases where it will go by the assumption that et minus 1 and it is equal to 0. So now we have this term, and we will have many terms like this. This we can take the common, and when we take the common over here, so what are the things that can be taken common is theta 1 sigma square epsilon. This epsilon should come down, so just ignore this. And what is left is here 1, here there is theta 1 3, theta 1 has been taken out, so you are left with theta 1 square, and likewise. This again is a case of infinite geometric progression. This can again, by using the common ratio and the first term, we can write it as theta 1 sigma square epsilon divided by 1 minus theta 1 square. Again, this process, this is a constant. It is not changing with time. So if theta 1 is less than 1, the process will fluctuate, agreed, but it will fluctuate around the mean, and because of this, the variance will be constant. So we have taken an AR model, and we have seen its mean is equal to 0, its variance is constant, and its covariance is also constant, meaning thereby this process is a stationary process. The only thing which is here problematic is this type of series which has a 0 mean. It rarely happens in economics, but nevertheless this is a demonstration of how to identify whether a process is stationary or not. Now we take the next model with a drift, that is, we incorporate a drift parameter over there. So incorporating a drift parameter means we are giving mu. Understand again, mu is not the mean of the process, rather it is the variable which determines the mean of the process, but it is not exactly the mean. So y1 is equal to mu plus theta 1 y0 plus epsilon 1, y2 is equal to mu plus theta 1 y1 plus epsilon 2. Now in place of y1 we incorporate this entire term. So when we open up, we can write it like this: y2 is equal to mu plus theta 1 u plus theta 1 square y0 plus theta 1 epsilon 1 plus epsilon 2. In general form, when we incorporate y3, y4, y5 and 6, we can write yt is equal to mu plus theta 1 mu plus theta 1 square mu plus increasing up till theta 1 t minus 1 mu plus theta 1 t y0 plus epsilon t plus theta 1 yt minus 1 plus theta 1 square epsilon t minus 2, and likewise we write this model. Now as t tends to infinity, again these two terms, as t tends to infinity, it becomes 0, and this one also, as t tends to infinity, it becomes 0. So both of these two terms, because it's a geometric progression, and what has happened just in the near past, it has a big influence, and what has happened at the distance past, and that distance is now becoming near to infinity, such a long distance, then obviously then we can say safely that becomes the impact of it becomes 0. So what we are left up with is this equation: yt is equal to mu plus theta 1 mu plus theta 1 square mu plus epsilon t plus theta 1 epsilon t minus 1 plus theta 1 square epsilon t minus 2. From these terms we can take mu common. Mu is common in first of the few terms, so we take mu common, bracket open, 1 plus theta 1 square, and the remainder of the terms are what we have seen earlier also: epsilon t plus theta 1 et minus 1 plus theta 1 square et minus 2. Now this can be written in the format of mu 1 minus theta 1 using the same algebraic manipulation. So yt is equal to mu divided by 1 minus theta 1 plus the remainder of the term, that is epsilon t plus theta 1 et minus 1 plus theta 1 square et minus 2. Here in this case We have mu, this is a geometric progression, so mu is the first term and theta is the common ratio. Now, if we take the expectation of this series 0, 0, 0. So, upon taking expectation, what is left is only mu plus y1 minus theta 1. That is only left, and respected everything apart from this, it becomes 0. So, now we take the variance, the formula of variance, expected value of bracket open yt minus expected value of yt bracket close and raised to the power 2. So, we have just now seen that what is expected value of yt is this term mu divided by 1 minus theta 1, and what is yt? Yt is this entire term. So, we write this minus this. So, ultimately what happens, this and this cancels out because both are similar terms. One is having a positive sign and the other one is having a negative sign. So, we are left with variance yt is equal to, we are left with only this epsilon t terms, epsilon t plus theta 1 epsilon t minus 1 plus theta 1 square epsilon t minus 2 raised to the power 2. So, when we open the bracket and incorporate power in all the cases, we have sigma square epsilon plus theta 1 square sigma square epsilon plus theta 1 raised to the power 4 sigma square. Now, when we have this sigma square epsilon, this square term is missing over here. Please note this correction. So, we can take sigma square epsilon common in all the places. What we are left with is 1 plus theta 1 square plus theta 1 4. This we can write it in the same using the formula for geometric progression, taking the common ratio and the first term. So, we write it as sigma square epsilon divided by 1 minus theta 1 square. So, this gives the impression that the variance of the process, it doesn't depend upon time, it's also a constant. Now, we check the third property, that is the third property of covariance. We check for regarding covariance. So, we write this formula for covariance as expected value of bracket open yt minus expected value of yt bracket close multiplied by yt minus 1 minus expected value of yt minus 1. We have seen before that yt minus expected value of yt minus 1, because the term, one time it is in plus, one time is it in minus, it gets cancelled away. So, this is what is left. We have just now seen in the previous slide. Again, yt minus 1 minus expected value of yt minus 1, we just take a lag. Here it was epsilon t minus 1, epsilon t minus 1, epsilon t minus 2, epsilon t minus 2, epsilon t minus 3. Now, we have to do the cross multiplication. So, we write the expected value of this first term and then the expected value of the second term we will be taking. Again, the same logic, epsilon t minus 1, those if they differ, if it's the error term and they are of a different period, their expectation becomes 0. So, what and so epsilon t, if we multiply with this 0, multiply with this 0, multiplied with this 0, theta 1 epsilon t minus 1, yes, we get the term. So, we get epsilon 1 theta 1 epsilon t minus 1 square, that is sigma square epsilon, and then this multiplied with this is 0, this multiplied with this is also 0. So, means when you take the expectation, et minus 1 and et minus 2 and et minus 1 and et minus 3, all them of 0. Similarly, for this term epsilon et minus 2, this is 0, but this there is a term. So, we get a term theta 1 square, there is 1 and here it is 1. So, we multiply. So, we get theta 1 cube epsilon e square, sigma square epsilon. So, we get these terms, and similarly if we have incorporated more values, as the values you incorporate, you will get the terms likewise. This again we want to define it for the overall function. So, what we can say, we can take out sigma square epsilon as common. So, what we are left with 1 plus theta 1 square plus theta 1 raised to the power 4, and likewise which we can write it as, using again our knowledge of infinite geometric progression, theta 1 sigma square epsilon divided by 1 minus theta 1 square, meaning thereby this covariance is also constant. It is not varying with time. So, we got the processes. We have defined certain, we have taken AR model, we discussed stationarity concept in relation to AR model. We have seen all the three, we have taken three variants of AR model, one the simple one, the second one with drift, and the third one with drift and no, we have not taken with the drift and trend, we have just taken with the drift. Trend is also, we will be stopping over here right now. So we have seen that in both the cases, the mean is constant and the variance is constant. So in this case, we do not have our process is stationary. If we want, now if you remember in yesterday's discussion, we started with these two graphs. This is the process, first one, zero mean. The first case was having a zero mean and constant variance. So hypothetical diagram can be drawn and this data will have this process. The second one, it was not having a zero mean, but it was having a drift parameter with it, but the variance was again constant. So it is, the series is not revolving near zero, but it is revolving at the point where it is mu divided by 1 minus theta 1. So these two are the cases, both of them are stationary. The mean either is zero or it is a constant, the variance is constant and the covariance is a simple AR model and AR model with a mean parameter. And if your value, now this all we are discussing with the assumption that theta 1 is less than 1. If theta 1 is equal to 1, if your AR process is such that your theta 1 is equal to 1, although it becomes a random walk model, but if you just put the value in the variance, it is very easy to explain that whether it is what is happening to the series. So sigma epsilon square divided by 1 minus 1 is 0, that is infinity. So it means if theta 1 is equal to 1, the process is non-stationary. And again another pictorial representation. So we see that in the first diagram, your this is less than 1, which is a stationary process. If your theta 1 is more than 1, the series explodes. And if theta 1 is showing this pattern, series is having an unit root and it is not stationary. This is a case of not stationary. Here we take a break. We will continue with our discussions on stationarity in our next class. Thank you.